favorite definition of work, and I'm not saying this is the best definition, it's actually probably one of the worst definitions, but my favorite definition of work is uh, the ability to use energy. Why is that not the best definition of work? Yeah. Oh. What's the definition of energy? The ability to do work. Yeah. So that's terribly helpful when the definition of work is the ability to use energy. Some books will actually define them circularly, and that's super not great. So we need another working definition for work. The secondary definition we're going to use here is the application of a force to move an object in the same direction. The application of a force to move an object in the same direction. Okay, mathematically represented, you guys have already identified that work is equal to force times displacement. Okay, units wise, we know that force is kilogram meter per second squared, and displacement is meters. Taking the product of those, we get something we've actually seen before. Kilogram meter squared per second squared. We've already talked about that in this unit, and that's a joule. So mathematically, work is simply another kind of energy. Okay? Work is what we talk about when we're taking a non-mechanical energy and turning it into mechanical, or vice versa, taking a mechanical energy and turning it into something non-mechanical, like heat. Okay? A couple of nuances here. First of all, in order for work to be done, the force applied to an object must be in the same direction and same dimension as the displacement, meaning that force and displacement must be parallel. Force and displacement must be parallel. So, if I take a pair of wooden blocks and I hold them here, am I doing work? Why not? No displacement, so no work is done. All right, I take this pair of blocks and I raise them to here. Have I done work? Yes, I've applied a force, I moved them to displacement. Okay, again, have I done work? No, why not? Right, sure, I'm applying a force, but it's not in the same direction the blocks are moving, therefore no work is done. Okay, how about now? Have I done work? Technically me, no. What force and displacement are parallel and in the same direction there, though? Gravity. So as I lowered the blocks, gravity did some work. I didn't. Okay? All right, so force and displacement must be parallel, and we indicated that they've got to be in the same direction. All right? Wow, I just completely drew a blank there. So if we want to take a look, now we're unpausing James. If we want to take a look at that question of if we had that object or that roller coaster car at the top of the first hill, and it's got another hill that's the exact same height, wouldn't it not make it over that second hill? And the answer to it was, that depends on how efficient the brakes, or sorry, not the brakes, but the bearings and the wheels are. And if there's being a lot of energy lost due to heat, which would be energy lost due to work done by friction. So if we want to take another look at that hill, here we've got these two spots. We said they were 20 meters high, and initially we were traveling at 2 meters per second. if we look at this and find how long the path is, and know on average how much frictional force applies to the cart, we can determine how fast the cart can be going, or if it'll even make it to the top of the hill. So again, initially we have mgh plus half mv squared for point A. I'm just going to mark this one A and this one B for the purpose of this. And set that equal to the gravitational potential energy for location B plus the kinetic energy for location B plus the work done by the time you get to location B. So just like any of the other energies we've worked with, work can be added and is conserved just like all of the others. Good? So from here, let's say that the average frictional force over the, we're going to go down, up. Let's say this is 100 meters of track is 1/6 the weight of the car. What's V at B? Okay. So another way of phrasing this is, will we have enough energy to even get to the top of this hill? Because in the video on roller coasters that we watched, the ball bearing on that curtain track didn't have enough energy to get to the top of the second hill. Now, there was an oversimplification that the guy in the video was making, having to do with what we call rotational kinetic energy, and we'll deal with that in January. But for now, let's just worry about friction. So to solve this then, I want to show that the work is some quantifiable value, and the work being done is the work by friction. So this is the force of friction times the displacement of the object. Force of friction is calculated as mu times, well, force normal. However, we're told that the frictional force over the 100 meter of the track is 1/6 the weight of the car. All right, so 1/6 weight is force gravity, so mg. Everybody good with that? In the problem, they tell us average frictional force is 1/6 the weight of the car. So force friction is 1/6 mg. Okay? Yeah. It's a little more complex than that. It's because there are some points where this is going to experience more normal force, and some places where it's going to experience no normal force. There's some factors that have to do with the components of that force normal throughout this entire segment. And it would depend on the exact inclinations. But yes, one of the components that goes into figuring this 1/6 is the mu value. We don't have to delve into exactly how that's generated because that requires some significant calculus. Does that answer your question? So this 1/6 isn't exactly the mu value, but the mu value is important for where this 1/6 comes from. Okay. Now working into the equation, what we've got here, mg h at a plus half m v at a squared equals mg h at b plus half m v b squared plus 1/6 mg times the displacement. And we said the displacement should be what? 100, because we said it was going to be 100 from here to here. I want to point out that the displacement we're using for calculating this work is the displacement over each segment of the path. If we just talked vertical displacement, here to here, it wouldn't have done any work. If we just talked horizontal displacement, we'd be neglecting the friction that occurred during the down and up segments. So we have to include that, and it's got to be our path length. Okay, so first of all, what do you notice about mass? Chances up. So we previously stated that for a roller coaster, mass doesn't matter. You're going to get the same ride. This holds true even when we start to account for friction. Even when accounting for friction, the ride is the same. So our masses cancel out. 9.8 times 20 plus half 2 squared equals 9.8 times 20 plus half v squared plus 1/6, 9.8 times 100. First of all, I can subtract these off. Those are gone. Okay. And by the looks of it already, I'm willing to say that this thing is not going to make it up that track anymore. Okay. So half of 2 squared, this is going to be 2, equals half v squared plus 1/6 of 980. Already, you can tell that you're going to get square root of a negative number, right? Because we're going to get that square root of that negative number, in this scenario, now that we've got some friction added, he's right, the car will not get back to the top. Neglecting friction, sure, it was able to get back there. And maybe with a more efficient car, oh, hang on. This 100, oh yeah, that's the displacement, that's fine. And maybe with a more efficient car, one that didn't have such a high ratio here, maybe it would have made it. But because this one's got enough friction acting on it, too much energy is being dissipated, it doesn't make it to the top. Okay? Let's look at a different location on this track. One of the other spots that we talked about was halfway up the track. So let's go another, let's say 75 meters. Actually, we're not going to make it there. Let's go a total of 75 meters. We're talking about this location. Sure. So now rather than trying to see how fast is it going at the top, let's try seeing, actually that's still not going to work. Let's see where it stops. So where does the cart stop? Okay. So we're going to change all this energy into work. So if we've got 9.8 times 20, gravitational potential energy times its mass, plus half 2 squared, kinetic energy times its mass, equals work 6 times 9.8 times d. So I've divided out the masses from all of these. And we're just going to see how far would it actually be able to travel and still have some amount of energy. So 9.8 times 20 plus half of 2 squared, so plus 2, times 6 divided by 9.8. At most, this cart could have made it 121 meters of track if it never went up. If it only traveled downhill and level. Huh? So what we're showing in this part of the example is that we can take gravitational potential energy, here we'll just put M there, kinetic energy, and turn it all into work done by some point. Okay, so all of this energy that we had dissipates into thermal energy. You guys saw this on the simulation you worked on. With the half pipe FET, as you turned on friction, the more friction you got, the faster things came to a stop, and the more energy was dissipated as thermal energy. we can just now calculate how much energy goes into thermal at different points based on the force of friction acting on that object. Questions on this example or what work is? Okay, there's one other concept for this chapter, and that is power. Power is the rate at which work is done. Work is done. Power is calculated as work over time, which is showing us that the units are joules per second. Which we don't bother saying joules per second. We actually have a different unit that you've all heard before, and it is what? It is what? Watts. Okay. And yes, I did need to make that pun. It had to happen. Okay. This is the same watts that you talk about when you talk about a light bulb. A 60-watt light bulb is using 60 joules per second. We can actually calculate the amount of work that you need to do in order to power a light bulb for 60 seconds, or sorry, for X amount of time, and what kind of mechanical work that would have to do, how many objects you'd have to drop from how much height, how much energy you can get from a hydroelectric dam based on the weight of the water that comes through the turbine. Because if we're talking about a hydroelectric dam, we're just changing gravitational and kinetic energy of water into electric energy, which we can figure out through power and work. I'm not going to go over an example of this one right now. Typically, power questions are incredibly plug and chug. We'll see some of them tomorrow when we work on some practice problems. For the time being,